Peter.
Okay, great. Okay, well, I'd like to welcome you all to the Statmos online seminar. And today we're pleased to have Montse Fuentes, who's the head and full professor at NC State University. It's kind of strange giving an introduction because everyone knows her very well. She's currently the PI and the director of Statmos, and so we're very happy to have her here to talk about spatial statistics for environmental health data.
Well, thank you, Peter, and welcome to this Statmos seminar. So the purpose of this presentation is to introduce statistical methodology in the context of working with environmental health data, in particular by taking advantage of the geographic information that we have for the health endpoints. Right now, with all the advances in GPS, global positioning systems, and GIS, information, we have been able to gain much more easily access to geographic information for public health data. So we certainly want to take that information into consideration in our environmental health analysis. So the work I'm going to present here is in collaboration with one of my former students, Josh Warren, now faculty at Yale University, Amy Herring, a professor at UNC, and Peter Langois. He is at the Texas State Health Department. This is a collaboration with that health department. So the environmental health application here of interest is working with adverse pregnancies and outcomes. In particular, we are working with birth defects, so more in a technical term, congenital anomalies. So what we are trying to understand is, in particular, linking these type of adverse health endpoints to potential stressors, environmental stressors in this case. We are interested in understanding better birth defects because they are the leading cause of infant mortality. They explain more than 20% of the infant deaths, and the incident rate is about 3%. The most common type of birth defect is cardiac defects. And that's going to be the focus of this research. From an economic point of view, it is quite expensive. We spend more than $2.5 billion per year just in hospital costs alone. Despite the fact that this is such a significant problem, we don't really have a very good understanding of the cause of this type of adverse pregnancy outcomes. Only in about 30% of the cases we understand what the cause is, and in those cases it's either due to genetic conditions in 20% of the cases or environmental conditions in 10% of the cases. So with that in mind, there is really a significant need to understand better what type of associations we have between these adverse pregnancy outcomes and other potential stressors. So in this case, again, the focus is on air pollution, environmental stressors. And the literature is very limited on that regard. So we do have few studies trying to understand the association between few pollutants, PM10, SO2, and a few of the birth defects. The analysis have been conducted separately, aggregating data primarily throughout the entire pregnancy or throughout one of the trimesters throughout the pregnancy. So there is need to conduct further studies that would give us a little bit better understanding of this potential link between exposure to air pollution and these birth effects. So with that in mind, the type of information that we are using, we do have geographic information for the mothers in Texas, again, a collaboration with the state health departments in Texas. So we have geocoded the residence for the mothers. And something that I want to point out in this study, so we are going to be using the residence of the mother at the time of delivery, so the geographic information of interest, trying to represent what was sort of exposure throughout the pregnancy. In this particular study, we have been able to evaluate the percent of mothers that were moving throughout the pregnancy, and it seems that in Texas, only about 30% of the mothers moved throughout the pregnancy between the day of conception and the day of delivery. And of those who actually move, most of them they stay in in a neighborhood in a very close proximity to the location of delivery. The information that we have from these birth records It's relatively limited, but we do have information from the mother and the father, race, ethnicity, education, age. For the infant, we know the gender, the birth weight, the pregnancy outcome, plurality of the pregnancy, and the number of previous live births. So this is just the density of the births in the state of Texas. And you can clearly see the areas that are more populated. So this is going to be a case control study. So we have two controls per case, and the matching has been done based on the mother's age, year of birth, and the infant's gender. And the birth effects that we are going to be focusing here are all of them heart related, and they are the three main ones, the atrial, pulmonary, and ventricular. So part of what we are trying to do is to model simultaneously these three different outcomes of interest, because we are working with real events. So we can gain much more power in really being able to study this link between the exposure of interest, the air pollution, and the adverse health endpoint by putting simultaneously together all the different sources of information that we have. So in this case, the three outcomes of interest. The reason why we are focusing on this state of Texas is because there is a cluster of birth effects in the southern part of Texas that is not very well understood. So due to that, it was a birth effects epidemiology and surveillance branch was established in Texas to gain a little bit better understanding of why we were observing this clustering of these unfortunately birth outcomes in the southern part of Texas, primarily in the Brownsville area. So we are working here with over 5,000 controls to 2,500 cases from 2001 until 2004. Again, the data have been geocoded, and we are now using the births that when the gestational age was less than 20 weeks. Okay, so this is the state of Texas, and here you can see on your right the subdomain of interest. So primarily this area in the southern part of Texas, Brownsville, is what is of great interest, but we are going farther north, and we include all the births going farther north, in particular here in the areas of Houston and also San Antonio. One thing that I want to point out is that there's no isolated events. So just because we have one particular case or one particular birth effect, that doesn't mean that we wouldn't have the others. So there are all sorts of different combinations. In some cases we have one of them, the ventricular. In other cases we have two. In other cases we may have the three of them. So again, it's important to model simultaneously these three different outcomes. With regard to the predictor of interest here, air pollution. So we're interested in understanding the potential association between exposure to particulate matter. Particulate matter is a pollutant that is currently regulated, and there is not really very good understanding of potential associations between the exposure to PM 2.5 particulate matter, the particulates that are very small with a diameter of 2.5 microns, which is about the size of the diameter of human hair. So again, this pollutant is currently being regulated, but what happens with the PM 2.5 is that the composition would change depending on where you are, because particulate matter is simply a mixture of air pollution floating in the atmosphere. So we could have more nitrate or sulfate depending on location, depending on time. So we here want to get a better understanding of what we're really being exposed to, which is really essential in the context of regulating pollution. So we are going to be looking at the different components, and I list here the more relevant components, or the most significant components of the total PM 2.5, and they are nitrate, sulfate, elemental carbon, and organic carbon. And we do have access to those components. The data being monitored and throughout the state, and in this graph you have the locations where we have the air pollution stations. So it's very limited, as you can see. We really don't have even information in Brownsville of what would be the levels of the components of the PM 2.5, what we call speciated PM, the different components. So we need to really seek additional information from other sources. So how we can fill these gaps that we have across the space and also across time, since the information for these pollutants is being provided every 3 to 6 days. So it's very limited information that we have, particularly in the context of being able to link the pollution to the health endpoints. We really need a little bit more information, a little bit more coverage across the space and time. So there are other sources of information. So we have information from deterministic models, what is called CMAQ. So this is an air quality chemistry model. It's called Community Multiscale Air Quality Model. So this type of deterministic model with input about weather, input regarding emission rates, and using some initial and boundary conditions, we are able to simulate what will be the levels of the different components of the particulate matter across the entire United States. So obviously that would be extremely helpful in the context of getting more information about the pollution levels, but these type of models, they need to be calibrated. So here we are using information from the monitoring stations to calibrate the models and to obtain what will be at any given location, at any given time, information about the levels of the PM 2.5 as well as the different components of the particulate matter. So with regard, so after giving a little bit of background for the problem of interest in the context of working with birth defects and trying to study the link to pollution. With regard to the work that has been done, it's been primarily non-spatial, so it's at a given location, trying to understand what is the association between the potential level of pollutions, and there are very few pollutants that have been used in this type of health models in the context of looking at birth defects, and the data have been aggregated either throughout the entire pregnancy or maybe through a trimester. So the analysis have been conducted separately for different pollutants and for different birth defects. So with all that in mind, what we are trying to do here, a little more ambitious, so we are trying to make sure that we take advantage of all the information that we have. Certainly, we want to borrow across space, across time, across birth defects, because the signal is very weak. It's a very rare event, so we can gain much more power by bringing all the different sources of information together. And we want to be able to make inference, not just with regard to aggregated exposure throughout the pregnancy. That's not very meaningful in trying to identify what are the critical times throughout the pregnancy will be more impactful to the exposure to a particular pollutant. So we really want to be able to make inference about specific times throughout the pregnancy where those exposures would have a more of an adverse impact. And we want to be able to understand this type of association between exposure to air pollution and the adverse health endpoint, how that association could change across the space and time. So we want to introduce a lot of flexibility in how we are able to model that type of relationship between air pollution and the adverse health endpoint, introducing general statistical model that would allow us to characterize how, again, that association changed maybe in a very heterogeneous way across the space, keeping in mind that the area, the geographic domain of interest, is very heterogeneous. We are working here with Texas, more rural and more urban areas. And we also want to make sure that we take into consideration, we characterize the uncertainty associated with the model and the data that we are working with. Okay, so with that in mind, in the first sort of attempt to write a model here to study a type of association, if we look at the type of outcome that we have, it's a binary outcome. They would take potentially the value of 1 when a pregnancy ends on a birth defect. So we call Y, IJ, the outcome of interest, Y represent pregnancy I, the mother I, and J, the particular birth defect of interest, taking into consideration that we want to model simultaneously the different birth defects as well as the different locations of interest for these mothers. So P would be the probability, so this would be a Bernoulli, so the P would be the probability that a pregnancy ends on that particular birth defect. So what we are working here is with a probed model, so Phi would be the CDF of a standard normal. So we're just trying to understand how this probability of birth defects could be explained as a function of either personal characteristics, that would be X in our model, so X are the mother characteristics and potentially other type of conditions. But here what is critical is to understand the role of pollution, so that's our variable C. So C would be the pollution levels at a particular location of interest, and we want to understand that association. So eta would be the parameter that will help us to understand what is the impact of pollution in explaining that adverse health endpoint. And we want to make sure that that eta parameter, the risk parameter, is modeled in a very flexible manner. We allow eta to change across space, time, across birth effect, and in a way that would be able to detect potentially signal at one location and maybe not and others, or in particular in some cases there are going to be potentially more critical, very short time windows throughout the pregnancy that will be more sensitive to the exposure of this air pollution. So in trying to introduce a very flexible model for that eta parameter, we would like to be as flexible as possible. So we are going to be using a non-parametric model within this Bayesian setup. The reason to work with within a Bayesian framework is that there are going to be quite a lot of different sources of uncertainty that we want to characterize throughout our entire sort of modeling and inference process. So with that in mind, we want to be as flexible as possible. So we are going to treat eta as something that is unknown. So we are going to put a distribution, a non-parametric distribution for eta. And we are going to start with a stick-breaking prior type of approach. So let me offer just very briefly a little bit of background about this type of non-parametric flexible models that we want to take. In this context, we are going to take it into a spatial, to a temporal, and to a multivariate settings. But let me start with the most simple scenario here. So we have G, this is the unknown distribution for eta, and we want it to be as flexible as possible. So G would take different values. So G is going to take the values theta. So G would take these values theta. With different probabilities. So the P's here would be the probability that the G would take some particular value, theta. So it's a discrete distribution, so you take different values with different probabilities, very straightforward. What do we call this a stick-breaking prior? Well, because all these P's, all these probabilities, they are going to add up to 1. And the way it's constructed, and in my opinion, this is the beauty of this approach, is in a manner, in a way that you can very efficiently be able to work with this mixture without having to worry so much about how many of these mixture components you need, which tends to be the most challenging aspect of working with mixture models. So the way this is constructed, you know when you have to stop, when you have sufficient mixture components. So let me explain that a little bit. So the reason why this is called breaking the stick or stick breaking is because you assume that you have a mass of 1. So that's the total if you add all the probabilities. So that would add up to 1. So that's like having a stick. So here, instead of a stick, I have a bow. So this would add up to 1. And this is the total mass. So we are going to be breaking this stick. So we break it, we cut it. So this is the first piece, so this is the P1, so this will be the first probability. So this explains a fraction of the total, a fraction of 1. So that's the first piece, P1. Well, you still have some left, so this is what we have left of the total mass. So this is what we have left, and we keep breaking the stick. So we break it again, so you get now the second probability. So I cut this string again. So this is the second probability, and this probability would explain a fraction of what it was left. And this is what it was left, and we keep breaking the stick until it gets to a point that there is not really more to break, or it's very negligible. So, but you know when that happens, because you know what you have left. So it gets to a point that, you know, there is just a tiny piece left. So that's negligible. So then you know when to stop. So here, if you look at the expression that we have for the stick breaking, each probability explains a fraction of what is left. So this V here would be a fraction of what is left, and what is left is this product here, that it may look as a very not friendly expression, but it's nothing but the probability that is not accounted yet by the previous component. So this is the stick breaking prior. So a very computationally efficient approach, because you know how much you have left. So for the most part, with a relatively small number of components, you might be able to explain all the distribution without having to go into algorithms to estimate how many components you need in a mixture, as the computationally very expensive approaches as a reversible jump and similar type of statistical algorithms. So, so now with a little bit more insight with regard to the components, the stick breaking prior, for the fractions of what is left for each one of the probabilities, the V's, what we call the V's, we tend to use a beta prior, and then we have some type of base distribution for the thetas. A particular case of the stick breaking prior is called the Dirichlet process. So the Dirichlet process is a stick breaking when the mixture goes all the way to infinity, and the beta priors are of a particular form. They have one of the parameters fixed. So we have only this second component alpha to estimate. So that's a particular case of this stick breaking prior. For the most part, we don't need to go to infinity. Usually with a finite m, and in many cases very small, we are able to explain the distribution. I want to emphasize that this is a discrete distribution. So in many cases, if we are working, and from a practical point of view, it's not really an issue because we can keep adding as many components as we need. But if we have a continuous outcome of interest, what we could do is just add error component, continuous random component here, epsilon. So so that way we work with the continuous outcome of interest, and here eta would be would have the stick breaking prior that we just have introduced. Okay, so that's a little bit of background about the stick breaking prior. Now, if we want to take it to the spatial setting, we need to put some spatial structure. And well, we have only two components here in a stick breaking prior. One is the values of the stick breaking prior, the thetas, and the other is the probability. So we either make theta spatial or the piece. So, but first, just a graph here to illustrate again. This is a stick breaking prior, so you can see this discrete distribution takes different values, different thetas, with different probabilities. So the way to, again, to construct it is you draw a value of theta from some base distribution, and then you draw a value of the V from the beta prior, and that would be the probability assigned to that value of theta, and you keep going. Okay, so now to take it to the spatial setting, there is some literature in to either put a structure into the thetas or to put it into the probabilities. So Alan Gelfand and his collaborators have been working quite extensively on this, and an initial approach would be to make the thetas a spatial process or a multivariate process. So in order to be able to do that, we need replications to be able to model the thetas as spatial components. One of the issues with this approach potentially would be, well, one is the fact that you need replications across across time, to be able to do that. And the other is that the probabilities of selection, the p's, do not change across the space. So you do have the same probability of selection everywhere. So in many cases, it's challenging to model this way heterogeneous spatial patterns because you have the same probability of selection everywhere. So a modification of that approach would be by having some type of clustering. So you can group some of the thetas and you can group some of the probabilities. So that will facilitate a little bit more of a jumpy type of a spatial surface. And then another possibility would be to just introduce a little bit more I think simpler structure by introducing a smoother across the space in a sense. So the thetas do not change across the space, so we don't need the replications, but the probabilities would change across the space, but in a relatively sort of simple manner. So the probabilities are being here the piece that we had before, but they are multiplied each one of them by a kernel function that is centered at a different node of interest. So that's all that we are doing, introducing a kernel function for each one of these probabilities, so that way the probabilities change across the space and would allow us to also have potentially quite a bit of heterogeneity. So let me just, before I introduce more the technical notation, let me just introduce a graph to illustrate what we are trying to do here. So this will be in a one-dimensional case. Here we're working in 2 dimensions, but let's assume that a space here is just 1 dimension. So, so our observations here are from 0 to 1, that's the spatial domain of interest. And I just want to show you how the probabilities will look like. The point I'm trying to make is that the probabilities change across the space. So how we do that? Well, in this case, we are working with 5 probabilities. 6 is whatever is left to make sure that they all would add up to 1. So we have 5 probabilities, so then we introduce 5 kernels centered at different nodes. So the nodes here will be 0.5, and you see that 0 and 1. So the first kernel will be centered here at 0.5. So as a result, you can see that the first probability, which is the darkest one, it would be the dominant one when you are at the location 0.5. If you move here close to 0, well, the dominant probability is going to be the 4th probability. If you move here more to the edge, here location 1, the dominant probability is going to be 0.5. So the different colors would explain what is the fraction that is being explained by each one of the probabilities at a given location. So it does change across the space. So that's how the spatial aspect is being introduced here. The probabilities are a function of where you are. As a result, the type of dependence that you have is non-stationary. So in the next graph, what we have is just the correlation between any 2 locations of interest. If this was stationary, the correlation that you would observe would be a sort of set of parallel lines along the diagonal, which is not the case here. If this was stationary in the one-dimensional case, if you look at the correlation between the location 0.3 and the location 0.5, to be the same as the correlation between location 0.4 and location 0.6, because they both are separated by the same distance. But in this graph, you can clearly see that the correlation between 0.3 and 0.5 would be different than the correlation between 0.4 and 0.6, so you end with a non-stationary, more general type of dependence structure. Okay, so now with all that in mind, let me just introduce the half model that we're going to be using to be able to make inference about the association between the environmental stressor and then the outcome of interest, that is multivariate binary. Okay, so the outcome of interest, taking the value of 1 when pregnancy I ends on birth effect J, and the P would be the probability here of interest, the probability of that particular outcome. So again, this is a probed framework. The reason why it's probed and it's not a logistic model is because we get full conjugancy in these settings. It's much more computationally efficient. The computational aspect is a key driver of everything that we are doing here, as well as being able to make flexible inference about the impact of pollution on birth effects. Okay, so we have the personal characteristics as the X of interest, but here is our pollution predictor. So we have several pollutants We want to model simultaneously the different components of the speciated PM, and that's a key aspect of our model. One of the challenges before working with this type of problems, it was to introduce simultaneously in a model different predictors highly correlated. So we are doing that here. We are modeling simultaneously the Q different pollutants of interest across space. So the pollutants will be observed at the location Si that corresponds to the coordinates for the matter. And then a key aspect here is the temporal aspect. So we are interested in making inference with regard to what happens different weeks throughout the pregnancy. So if we go with week D will be like the second week in the pregnancy. So what happens here is that the second week in the pregnancy for me will be different than the second week in the pregnancy for Elizabeth, who's here with me. So so we need to convert those. I don't know if you're pregnant, but if you were, we'll have different weeks potentially. So we'll have to make a transformation here to make sure that this week, second week, week D, is transformed to a calendar week. That's when we observe the air pollution. So this is the calendar week for the pollution exposure. This is the location of interest. This is the pollutant Q of interest. And now we go to the risk parameter, which is the key here. That's what we are trying to make some inference about and estimate across space, time, and pollutant. So this is the eta parameter changes with the week of the pregnancy, D, the pollutant of interest, the birth defect of interest, J, as well as the location. And when we make inference about the location, it could be either the point location of interest, the actual residence, or it could be geographic, a different sort of resolution of interest. Maybe we are interested in making inference what happens at the county level, census tract. So that's why I have the B here. This would allow us to work with whatever spatial resolution of interest we are interested. Okay, so so now the eta parameter is the risk parameter. So this is what is the key in this type of environmental health analysis, being able to make inference about eta. So eta again becomes a vector having information about the different pollutants, J, the different times throughout the pregnancy, the different birth outcomes, J, and the different pollutants, Q. Okay, so now we are going to use a stick breaking prior, a little bit more complex than what we have seen before because of the high dimensionality and the different type of dependence across the space, across time, and between pollutant and birth effect of interest. So eta would have a stick breaking, the case for a kernel. We're going to be working with kernel functions. So let me try to give a little more insight with regard to how we characterize this sort of complex, high-dimensional, non-parametric prior here. So this stick breaking is going to take different values, different thetas, and again they change with pollutant and with birth effect, and they're going to change across space and time. So the probabilities are going to change across space and time. The way we make them change across space and time is the same type of expression we have seen before for the stick breaking prior, but we multiply that by a kernel. Here the W is simply a kernel-centered some nodes of interest across space and time. It's a little bit higher dimensional kernel, but we are working with tensor products of kernels, so it's a temporal kernel multiplying a spatial kernel. So that's a relatively simple structure. And then the thetas, so now the thetas, they explain the relationship between the different pollutants and the different outcomes, the different J's, and they also change across the space and time. So they're going to have a multivariate normal prior, but explaining that dependence across space relatively in a simple manner. So this sigma is a parametric spatial covariance. So the sigma t is another covariance that explains parametric, also explaining the temporal dependence. And then this other sigma explains what is the dependence between the cross correlations between the anomaly groups, the birth effects, and the different pollutants. So it's separable, so it's relatively simple structure. So we just have the Kronecker product of the different covariances. So it's really as simple as it could be. However, it's not gonna, the fact that is for each one of these mixture components, we have a simple model. That doesn't mean that at the end we end with this very sort of simple separable model. This is gonna introduce a very flexible, general, non-separable spatial temporal structure. Non-separable in the sense that it's not necessarily gonna be just product of different components. Even if the actual mixture components have this really simple structure, at the end, the overall dependence structure is gonna be very flexible. Okay, so then we have these etas. So again, the etas would take different values theta with different probabilities. So that's all that we have. So this is the stick breaking structure that we introduced. The probabilities change across space and time with the kernels, as we have seen, and the thetas, they change with pollutant, they change with the birth effect of interest, and they change also across space and time. Something that I want to mention without going into a lot of technical detail, but I do want to make the point that even if this is a very simple model to explain the dependence, by design, because we want something computationally efficient, we also needed something that was going to be flexible enough, and it is flexible in the sense that even if all these models that we are working with, they are separable, they are modeled separately, the space, the time, they are parametric stationary models that we are working with, in the sense that the spatial dependence that we introduce in the sigma covariance is simply function of the distances across the space. At the end, the type of dependence that we have, if we look at the conditional dependence, without again going into all the technicality, I just want to emphasize that it's going to be in general non-separable, it's going to be in general non-stationary. And you have the expression here, how it's going to look like. So this dependence, this is not a Gaussian process, so just looking at the second moment is not sufficient, but it's interesting to understand what type of dependence structure is introduced here. So you can see just by looking at the expression that this is a function of where you are, the location of interest. This is a function of the time of interest. So it's not simply just function of differences across two different locations or differences across time. However, if you look in an unconditional manner, you would like to have something that resembles the relatively simple models that we started with. So if we look at the unconditional covariance, the structure that we have here is actually fairly easy to evaluate. And it's a function of the kernels, the kernels, the priors obviously that we are working with. So the kernels determine here where we have a gamma is just a function of the kernel. So it really depends what type of kernel you are going to be working with. And I'm going to give you examples of how the covariance will look like depending on the kernels, which is nice to see that, the transparency with regard to what different kernels, what type of covariance structure you would end with. So just as an illustration of the role of the kernels, let me just show you what is the expression for this gamma, which explains the covariance, as a function of the different kernels that we have. And the A's and the B's are the hyperpriors for the probabilities, the betas, the hyperpriors and the betas. So, so here if you work, the type of kernels that we have been working with are primarily uniform kernels or exponential kernels. And then you can see that they end, if you have a uniform kernel, then you end with an exponential type of covariance. So you can see the relatively simple expression of the covariance that we end having as a result of working with this type of kernels. But again, flexible enough, general enough. Okay, so now let's move into a simulation to understand, what we are gaining by working with this type of framework. So what I would like to show you is how this model is going to perform in a situation where, well, in different type of settings. So we are going to be comparing the general model that we introduced here, the non-separable, non-stationary, non-Gaussian that is being obtained as a result of working with this spatial temporal multivariate stick breaking approach in this probit setting. And then as a little bit simpler particular case of that one would be still a stick breaking, but well, in this case, no, we're going to be working with a Gaussian. So we want to evaluate, the impact of working with the stick breaking, no Gaussian, versus just working with a multivariate Gaussian, probably the default for many of us, which would be separable stationary. So we model space and time separately. We sort of multiply both covariances, and they are both exponential parametric covariances. Okay, and then we compare that with just a probit, a multiple probit. So there is not a spatial or temporal dependence. So we assume independence between space and time, but we do characterize, the dependence between the pollutants and the birth defects of interest. So it's a multiple probit. So we model the different outcomes simultaneously. Okay, so those are the three models to compare, and we're going to be working with different settings. So we go from setting 1. So in this graph, just to illustrate quickly the results. So we look at the MSE aggregate across the space and time on the vertical axis, and on the horizontal axis, we are going to compare 3 different settings, 5 settings, 1 to 5, that they're going to increase in complexity. So in setting number 1, we are looking at the independent model in space and time. We want to make sure that this relatively more complex, in a sense, model that we are proposing here can do a really good job explaining the most simple type of a scenario. And then we move to a Gaussian setting that is separable and stationary. Then we move to the non-stationary case. We move to the non-Gaussian non-stationary, and then to the non-Gaussian non-stationary non-separable setting. So what you can see here, the blue line is the proposed model, model 1. And what you can see is that in the first case, when we have independence, so it does as well as the others, but as you increase the complexity, then there is a very significant improvement in the results by working, or pretty much it's emphasizing the need of this more general model as we increase the complexity. So if we look at the actual MSEs, so you can see that with model 3, there is a reduction of 50% in the MSE. Okay, and the coverage, so we don't have issues with coverage in any of the 3 settings. Okay. So with regard to the simulations, before I move now to the application, so this model has flexibility, it's computationally efficient, but it's able to produce similar results when we are in the most simple setting. But obviously, as we have more complexity, as we tend to have in real life, there is critical need to have this more general setting. We significantly outperform any of the potential competitors. Okay, so now if we go to the actual application, and what I'm going to do is try to work with a very similar setting as what we had in the simulation to compare different models to see when we go to reality here, when we work with the real data, what do we need, or what are the advantages of working potentially with this more general model. If we look at the DIC, which I probably wouldn't recommend, is not necessarily appropriate for this type of mixture setting, so we gain, so there's some gain by working with our framework, but I would like to really look more closely at different, more appropriate type of model adequacy checks in this setting, and we certainly would do that. With regard to the impact of different covariates, so here we are looking at the atrial, pulmonary, ventricular birth effects. So it seems that white mothers, they are at higher risk of any pregnancy with birth defects. Also having more than one fetus increases the risk, and it seems it's more likely to happen over the summer. So this is pretty consistent across the different birth defects with regard to relevant personal characteristics. Then with regard to evaluating, going beyond the DIC as a check for the, how our model compares to others, what it should be, I think, more natural to work with in this type of setting with binary outcomes would be to work with the residual discrepancy, Pearson residual discrepancy, in which we compare our outcome of interest, which is the Y, to the probability. And so we calculate the total, so we aggregate that across the different birth effects and the different mothers, so that would be the total discrepancy here. So in our Bayesian setting, the way to compare different models would be to looking at what is really from the data, what is the the posterior for this discrepancy versus the predicted posterior. So if we compare these two density functions, they should really be the same if we have a good model. So that's the bottom line. So if we look at the predicted posterior discrepancy versus the one from the data, these two should be similar if we have a model that really characterizes or represents well the data that we have. So that's what we are going to do. We are going to compare those type of density functions in three different settings. So setting number one is our proposed general model. Setting number two is probably what you would do if you want to characterize a spatial temporal dependence. Probably default would be to work with a Gaussian stationary separable model. That would be model 2, and then the third one, the multiple probit. So if you compare in each one of these graphs, model 1, model 2, and model 3, we have the discrepancy for the observed data versus the predicted one, and they really still look very similar unless the model is not really a good model for your data. And you can see that that's the case in model 1. They both look very similar. The two box plots will correspond, with the simulated values from both densities, and at the bottom you have the two densities being compared, and they look very similar. This is more of a visual analysis, but you can see it's really quite an issue when you go to model 3. So model 3 doesn't seem to be a very appropriate model for the type of data that you have. If you look at the two densities, certainly they are not on top of each other, right? In particular, you're looking at the tails. Maybe another way to, in a more analytic manner to look at it, you really can just go and look at the actual values of the two densities. So here for model 1, on the left we have the density values that will correspond to the observed discrepancy. This is the predicted, and you can compare, number by number to sort of see a little more closely the differences. And what I want to point out, it is an issue once you get in particular to model 3. If you look at you have a value 0.003 versus 0.8, and also with model 2, you have a value of 0.1 versus 0.6. So there are some serious issues here with regard to the use of these type of more restricted models for the type of data that we have. But when that is a little bit more apparent is when we go and we estimate our risk parameter, which is the key in this model. So here what we have is, again, we are working with binary data, so we are looking here at the score function. So what we have here on the vertical axis here, the z-score. So what that's telling us, when that is positive, that means that the probability of that birth effect, in this case we're working with pulmonary, with regard to the exposure to nitrate in this case, is significant. So if it's positive and significantly different from 0, that means that we have a significant positive impact of pollution on that particular birth effect. And if it's negative, that z-score is negative, that means that the impact of pollution is actually negative, so it's actually good for human health. So that's how to interpret the graph that I have here. So so what you see, so the vertical axis is the z-score, the effect that we're trying to estimate, the magnitude of that effect. And then on the horizontal axis, we have time throughout the pregnancy. We have been working with weekly data. Beyond that, I mean, we certainly could implement this with the daily level, but the information at the daily level is not very accurate. Trying to know for sure conception and all that the accuracy is not really quite at that level of resolution. So we're working with weekly data. And with regard to the more critical time, I could show you the entire pregnancy, but the heart, these are heart birth effects, and the heart is being developed between week 3 and week 8 during the pregnancy. So those are the weeks of interest here, and those are the ones that I'm showing you this graph, week 3 to week 8. So I'll show you what happens here in this particular location, Brownsville. I'll show you other locations. This is for the pulmonary birth effect. This is for nitrate. So we are trying to understand this particular geographic domain. Again, the analysis has been done simultaneously across the space, but I'll show you what is the risk at this particular location if we compare Model 1 versus Model 2 versus Model 3. And the dot here, the red dot, represents what is the median of that estimated effect, and with a 95 prediction interval here for that effect. So, so if you look at the estimated effect, and we have the same scale in each one of the three graphs, what you can see is sort of the same type of trend that we see Model 1, Model 2, and Model 3. What is clear is that if you go to Model 3, this is pretty easy to interpret and not very surprising, is that nothing is significant. So that's what it tends to happen when we work with birth effects, that if you work with what happens at a particular location, you don't tend to have power to make inference with regard to what would happen for certain weeks throughout the pregnancy. You can see that you have wide confidence bands, so so it becomes difficult to make that type of inference. You need to borrow information. So a way to borrow information across the space is with Model 2, but here you are clearly over-smoothing. So yes, you reduce the bands, but everything becomes too flat. So you need to introduce a little more flexible model that can potentially allow a little bit more heterogeneity in that type of spatial dependence. And then that's when you go to Model 1. And things will now appear to be significant. We already know that this is a more appropriate model for the data. We have already checked the model adequacy, and that's when we see things being significant. And we are in a position of making inference about what is the critical windows throughout the pregnancy that will be more impactful with regard to the development of this birth effect. And then you can look at a different location. This is San Antonio. This is the ventricular birth effect. This is elemental carbon, same story. And if we are able to understand what weeks, which, you know, this is week 3, very, very early in the pregnancy, probably when the mother that's Statmos is pregnant, and that's the most critical time. And again, you wouldn't be able to see any of that, and that probably explains the lack of literature on that regard. You wouldn't be able to explain that if you just go and do the analysis without borrowing spatial information. That would be the Model 3, or just with the borrowing in a very simplistic manner with our separable Gaussian spatial prior. Very similar story, San Antonio, atrial, nitrate, and looking at, again, Brownsville for nitrate at atrial, very similar story. We tend to see, you know, significant effects. Primary tends to be week 3, in some cases it's more week 7, depending on the pollutant of interest and the location too. And the last one, this will be organic carbon. So you can see it's always the same with the spatial process. Probably what would be the default for most of us, you don't see anything anywhere. And the other one with the multiple probit will be probably the default type of model in epidemiology. You don't see anything anywhere either. So, so with this, just to wrap it up, first we made clear diagnostics to make sure that the model that we were using, it was an appropriate model for the data, and not only that, but that was the only one that it was outperforming, but it was also the only one that was able to really help us to detangle the noise from the signal and allow us to understand better what are the weeks that are more impactful with regard to the impact of air pollution on these adverse pregnancy outcomes. So this is not just a model in the context of looking at these environmental health problems, but it's certainly a very flexible model that can allow us to explain multivariate spatial temporal data in a very computationally efficient manner. These are very simple mixture models, and each one of the components is relatively simple, or certainly it has the simplest type of structure that we could introduce. And it allows us to make inference about the change across space and across time of the risk of developing this adverse health endpoint due to exposure to these environmental stressors. Furthermore, the results, they really show clear evidence supporting the link between exposure to air pollution and these adverse pregnancy outcomes, helping us to get a better understanding of the impact of pollution on birth effects, and helping us to continue educating our pregnant population with the purpose of trying to mitigate this type of adverse impact of pollution on birth effects. Any questions?
Thank you. Very interesting. So, oh, that's it's the first time we actually have an audience, so we actually have clapping. So that's very good. So thank you. And there's some claps on the virtual. So, so the microphones are enabled. If you want to ask a question from a microphone, as long as you've asked enabled permission, you can click on that. The other option is just to go to the chat window and type. So Uke Chicago is typing at the moment. But others, feel free to type in and ask your questions.
Well, first, are there any questions here?
Okay, so U Chicago asks. So U Chicago asks, does allowing effects of pollution to vary spatially have a biological explanation?
Absolutely, yes, because we are working with different birth effects. So the exposure could be different depending on where you are. The sources will be different, in particular when we are putting together rural and urban areas. So we really are looking at different sources, and that's why it's critical to allow it to change across the space, because it would allow us to really understand better what the issues are and how to potentially be able to mitigate them.
Great, thank you. Paul Sampson is typing. I'm guessing there's a question there.
Audience here to ask something?
Last one.
This is Armin.
Yes, hi. The type of covariance that is produced while it is non-stationary, it seems to have a very particular structure, the one that you showed. So does that make any sense geographically? Probably not.
Yes, so it does depend on the type of kernels that we are using, but it does have a lot of flexibility to change rapidly across the space or not, and it's pretty interpretable too. Locally, when you look at you can look at the conditional or the unconditional covariance. The unconditional covariance, it was quite interpretable. If you use with this type of uniform kernel, you then locally get this exponential behavior. So it does have some nice interpretation, but primarily it allows you to change as rapidly as you may need across the space.
Okay, thank you. Paul asks, U Chicago beat me to my second question. My first question, is exposure based entirely on 12 kilometer CMAC? So climate, this is a very coarse. You have many coefficient effects varying at a small spatial scale, perhaps, at a smaller spatial scale, perhaps related to the true spatial variation in exposure at a smaller scale.
A comment, yes, is based on 12 kilometers. With regard to speciated, we wouldn't really have higher resolution than that. Even working with the monitoring data is very sparse. Furthermore, I have worked with 4 kilometers resolution, and it's a little bit problematic in the context of working with health effects. 4 kilometers potentially characterize worse what you're being exposed to. That's been my experience in working with that type of data, because you move around. So remember that we are keeping fixed whatever location for the mother. So assuming that the mother is not moving more than 1 kilometer, it's probably more unrealistic to think that it's going to be in a vicinity of 12 kilometers. So by going to high resolution, in previous analysis that I've done, it wasn't really more informative with regard to the exposure that you have, unless you have, you're able to track the individuals across time, and we have done some of that. But in this context, going to high resolution, it wouldn't really help us.
Great. Any other questions from people?
Joe Guinness is here in the audience, and he has a question.
How did you decide?
Okay, speak up.
How did you decide which demographic covariance to include?
Well, it was limited what we had. We had information about education, race, and it's not that we believe that those would be the cause of what we observe, but there are prospects for other really relevant things with, nutrition. Those tend to be the really relevant covariates. So working with relatively limited information, but the education, race, age, tend to be in collaboration with the epidemiologists that we have been working with, that they seem to be the most relevant type of information for this type of health endpoint.
Great. Any others? So we got Glasgow Uni 2. I guess that's what happened after Glasgow Uni 1. I don't know what where the 1 went. Hello, I would like to ask this question. What's the value of Q, the number of air pollutants?
So in this case, we were working with 5. We had ozone, elemental carbon, organic carbon, nitrate, and sulfate.
Great. Oh, some more question.
I have another question.
Just while that.
Armin, while they
Yes.
type.
Sorry. So another curiosity is in terms of the covariance. So you're trying to relate this to air pollution, and I don't know if South Texas is a particularly polluted area.
It is.
But could this problem have to do with not where these women live, but where they work? Is there any information on that? Maybe they work in agriculture and they're just exposed to pesticides.
Yeah, well, but that would be characterized with the exposure. So this area in Texas there's very high pollution. They tend to be out of compliance, the border with Mexico. And it was observed a very high number of birth defects. It's true that the exposure in the working environment is very relevant, and we do not have that. But the geographic information will give us a pretty good understanding of potentially what they're being exposed to, in particular in these areas in the border with Mexico, where we understand that there are issues with the air pollution.
Right, and there was one more question. So from Glasgow, it said, okay, thank you. Are the Q air pollutants assumed to be uncorrelated?
No, not at all. They are correlated. The correlation is being introduced in, with a Wishart prior.
Okay. Great. Okay, any other questions? Or okay, thanks.
Thank you.
All right, well, let's thank Montse again. Thanks for taking time out. If you're in a
Yes, Peter?
If you're in a group of multiple people, please let me know your attendance. So this is the end of the Statmos seminars for this year. I guess this is the end of season 1 in some sense. And in the new year, I'll announce season 2, and we might take a little track differently. But we'll take a break for a little while, enjoy your holiday, and then we'll get back and plan out season 2. Okay, thanks a lot, folks.
Thank you. Thank you.
Bye-bye.
Happy holidays.